Hello everybody, welcome back to the Pythagoras channel, and today for the first video we are going to be going over how to dissect a polynomial. Right here I have a polynomial shown above. You set it equal to 0 to find when its zeros are, and what we want to do are we're going to go through a few steps to get through here, and we're going to go over a few theorems, rules, and useful tips to get you to your answer. So let's do this. What we can do here is, first thing you notice, all these terms have an exponent. We can take an x out. To factor it out, we just bring the power down for each of these terms. So x to the fifth minus 3x to the fourth minus 6x cubed plus 10x squared plus 21x plus 9. And then this equals 0. And now what this also tells us is that this, since this is going to equal 0, the zeros that we are finding are not for this polynomial. So what I will do over here is I will define a function f of x equal to that inner polynomial there, which is x to the fifth minus 3x to the fourth minus 6x cubed plus 10x squared plus 21x plus 9. Apologies if you can't pull this here. But now what we are going to do is we are going to apply first rational root theorem. Rational root theorem states that the possible rational zeros of a function are going to be all the possible factors of this divided by all the possible factors of that, positive or negative. Which means, well, allow me to make a section, rational roots here. And what that tells us is that our rational roots we can write as it's going to be the factors of 9, 1, 3, 9, all plus or minus. And these are known as the p's, and we're going to divide it by the q's, or the factors of the leading coefficient of the highest degree term, which is 1, and that's just going to be 1. And what that means, that implies that our possible zeros could be plus or minus 1, plus or minus 3, plus or minus 9. If this were to have fractionals, if this was a 1 and a 2, we'd have 1/2, 3/2, 9/2. But right now, we only have 1 as our leading coefficient. So that is all the values we should test. Next thing we want to do is consider a very useful thing called Descartes Rule of Signs. And what that tells us is whether the zeros can be positive or negative. So let's check that. So let's test here. So what we do to find those zeros is, for Descartes Rule of Signs, you find the sign changes. So we have one sign change here, because we go from a positive x to the fifth to a negative 3x to the fourth. And then we have another one here, because we go from a negative 6x cubed to a positive 10x squared. So we have two sign changes. And now what I'm going to do is I'm going to create the chart, because we're going to do this for positive. We're going to do another thing to find it for negatives. And what we can see here, we have, pause, and for imaginary, and here's the total. And what we just found out is that since we have two sign changes on the original function, what that means is that we can either have 2 positive zeros or 0 positive zeros. And I'm going to write this again for our, when we make the negative value. And that means also, let's not forget that since we are working with a 5th degree polynomial, we are going to have 5 potential answers. So that means the total number of roots here is always going to be 5. So 5, 5, 5, 5. And now what we do here is, how do we find the amount of negative zeros that we could possibly have? What we want to do is we want to evaluate f of negative x. So let's do that. F of negative x equals, and we're just looking at this inner function right now. So it's going to be negative x to the fifth minus 3 times negative x to the fourth minus 6 times negative x cubed plus 10 times negative x squared plus 21 times negative x, and then we have our constant plus 9, and this is still of course equal to 0. And what else? And what we are going to do here is another And that means we can write negative x to the fifth. A negative number raised to an odd power is still going to be negative, which means we just have negative x to the fifth. An odd negative number raised to an even power, however, is going to be positive, which means we're going to have minus. This is going to be positive, negative, negative times positive, negative, minus 3x to the fourth, and then negative times negative, we have positive 6x cubed, and then we have negative, this becomes positive, so positive times positive, 10x squared plus, and then this negative times positive, negative, so minus 21x, and then our constant again, plus 9. So what we do now is we are going to just count the amount of sign changes in f of negative x, which is this goes from negative, no change, negative to positive, that's 1, positive, positive, not a change, positive to negative, that's 1, so that's our second one, and then negative to positive again, that is our third one. Now, you see, we have 3 sign changes, so we have 1, 2, 3, and this is the f of negative x, which means that we can either have 3 negative roots, we're going to write 3 here again, or 1 negative root. And what that tells us is that we should most certainly try a negative value because we are guaranteed to have at least 1 negative root. And now what we're going to do, we're going to find how many possible imaginary roots we could have. And while this might not seem useful, it's just important to keep in mind so you know if you're not finding any zeros, that's why. So what this tells us is all these numbers have to add up to 5, right? So 2 plus 3, that's already 5. What plus whatever is 5. 5 plus what is 5? 0. 0 plus 3, that's 3. 3 plus what is 5? 2. 2 plus 1 is 3. 3 plus what is 5? 2. And then 0 plus 1 is 1. 1 plus what is 5? 4. So what that tells us is that these are possible imaginary roots. Now, let's go back and consider actually solving this polynomial. Now, we have our rational roots, and we are going to start testing our zeros. So let's begin by first evaluating what we know we have to have of, which is a negative 0. And for this, I will say it's nice to choose an intermediate value, and I'll show you why. So we will choose the value of negative 3. So let's test. And now we have quite the large polynomial, and we are going to do this through synthetic division, which, if you do not know, I will be making a video on soon. And so, well, we have 1, negative 3, we just copied down our coefficients, negative 6, 10, 21, and of course, 9. We drop this down, and now we have 1, negative 3, then this is going to become negative 6, negative 3 plus 6, this is 18, this is going to be 12, this is negative 36, remember, multiply, add, and then 10 minus 36, negative 26, 3 times 26, that is going to be 78, yeah, so this is going to be 78, don't have quite the space I need, and then 21 plus 78, that is 99, minus 3, negative 3 times 99. Oh, let me just make some space here. And so, negative 3 times 99 is, of course, going to be negative 267. Then 267, add these, this is just going to be negative 258. What that tells us is we can notice something about the signs of these values we were given. They alternate positive, negative, positive, negative, positive, negative. What that tells us is that negative 3 is in fact a lower bound. And let me just write that down. Lower bound. And what that tells us is that when we have a lower bound, that means we should not try any zeros that have a lower value than negative 3. And what we can see is that means we can eliminate negative 9. So that means we don't even have to consider it at all. So what that does is it gives us fewer things to work with. Now let's move our work to over here. Let's think of another negative value. We only have one more and we're guaranteed. So we know negative 1 has to be a 0. But let's find it. So course, synthetic divide. And we get 1, negative 3, negative 6, 10, 21, 9. Then what we do here, 1 is going to be negative 1. Negative 3 plus negative 1, negative 4. Negative 1 times negative 4 is going to be 4. Negative 2, 2, 12. Negative 12, 9. Negative 9, 0. And as we can see here, we have find our first zero. Except, of course, including x equals 0 up there for the original polynomial. Now what we're going to do is we're going to write this down because these are coefficients of another polynomial of the 4th degree. So what that means is this is going to be x to the 4th minus 4x cubed minus 2x squared plus 12x plus 9. And what that tells us is we should continue looking for more zeros. Because the real goal, if we reduce this to a quadratic, we could potentially use the quadratic equation factor. So let's get continuing with our goal, and let's evaluate another possible answer. We already tried our negatives, so let's see if any positive zeros would happen to work. And it's always safe to go with a nice intermediary, so we're going to go with 3. And now what you can do is the zeros of our x to the 5th polynomial is also going to have the same zeros as this x to the 4th polynomial, which means we can just plug in these coefficients and have a little bit easier work with us. So that means we can do 1, negative 4, negative 2, 12, and 9. So what we see here, 1, 3 times 1, 3, negative 1, negative 3, negative 5, negative 15, 3, and then negative 3, and then we get negative 9. That's another 0, which is pretty nice. Now what we have left here is, of course, a cubic. So I'll write that down. Over here we have x cubed minus x squared minus 5x minus 3. Now what we have here is a cubic, and which we cannot sadly factor by grouping, which means we're going to have to keep on testing zeros. But before we continue to do that, let us write down this. And we should keep track of our zeros as we've gone along, which I will do as of now. So one thing we know, x equals 3, that's a 0. X equals negative 1, that's also a 0. Oh, negative 1. And don't forget about our first one we found right off the bat, x equals 0, which is also a 0. And now what we're going to do is I am going to have to erase this side so we have some more room to work with, and just have it remembered that we did find negative 1 to be a 0. And what that means is we are going to take this, and then we are going to start trying some other factors. But let's consider rational root theorem and, of course, Descartes. One thing we should notice, this is negative 3. 9 is not a factor of 3 plus or minus, which means 9 should not be a value we should waste our time testing for this, which also means that we only have 3 possible options, since we already know negative 3 is a lower bound, so it's not that. So we have negative 3, not negative 3. We have negative 1, 1, and 3, which means we can also narrow down which ones to choose by Descartes. If we look at this, we have 1 sign change in the positive version, which means we are guaranteed 1 positive root. And what that means is, for the highest chance to get it earliest, we should choose a positive root, which was left with 1 and 3. And typically 1 is a close thing to work with. So let's just go through it. And we can use the coefficients of this cubic, of course, which is 1, negative 1, negative 5, and negative 3. And let's go through this quick. 1, negative 1, 0, 1 times 0, 0, negative 5 times 1, negative 5. This leaves our remainder of negative 8. So we did not get 1 as a 0. Let us try our only other option, which would be smart and guarantees it is 3. So we just have to get the form out of this. So of course 1 minus 1 minus 5 minus 3. Then we bring this down, and of course we get 1 times 3. This is going to be 2, and then 3 times 2 is 6. This is going to be positive 1, not negative 1. And then 3 times 1, 3. This is 0. And here is our last polynomial that we have, which is x squared plus 2x plus 1. Now, of course, let's keep track. X equals 3 is again another 0. So we have to write that on our list. And now we are left with a quadratic, which, if you recognize, this is very easily factorable. It is just a binomial squared. And that binomial would be x plus 1. So we can see x plus 1 squared, which means x equals negative 1 is a solution not only once, but twice. So we have to write x equals negative 1 2 more times. So x equals negative 1, x equals negative 1. So here we have our solutions. We have all 6 solutions to our original polynomial. And what we are going to do now, as of course, we are going to write this in factored form. So here's how it would work. So we do x times x minus 3, because we always do the minus. So this times x minus 3 again. And then we have negative 1, negative 1, negative 1, which means we're going to write x plus 1, x plus 1, x plus 1. And of course, this equals 0, correct? But now what we're going to do is we can compress this a little, and we can make this as x times x minus 3 squared times x plus 1 cubed. This of course equals 0. And here we go. This is our final answer. Were you to multiply this out, you would get that polynomial right over there. And that right there, guys, is the video on polynomial dissection. Thank you for watching, and I hope you guys enjoyed the first video on this channel. Hope you took something away from it, learned some stuff like lower bound. Sadly, we could not get into upper bound theorem, which, quickly going over, it would be an upper bound if all of these were positive. And that's just one thing about upper bounds. And thank you guys for watching so much. This is it's great to see that you stayed until the end.